topic 10 is about solutions and solution stoichiometry. I want to look at defining concentration first off. Now, what we'll find is that you can easily measure out a gram of material, maybe 1/100th of a gram, maybe even a milligram, a millionth of a gram, fairly easily. However, as I hope to show you, that dealing with solutions can often be a very quick way of arriving at very small quantities of material, providing, of course, that material dissolves in water and you're interested in the water solution of it. Let me start off by defining what I call the concentration of the material. And to a chemist, the concentration is very specifically what we call the molarity. And it is an amount in moles per litre of solution. So the concentration of something is a number of moles in a particular volume. The volume we choose is in units of litres, moles per litre, molarity. And like anything we've seen in stoichiometric calculations, we're dealing with relative numbers of molecules here. So the concentration is associated with numbers of molecules rather than with mass. I'll show you an experiment in one moment, but what I'd like to do is just go through a couple of the examples of this topic, and perhaps we start with example 1, where the scenario is what mass of sodium chloride is present in 500 mils of NaCl solution of concentration (2 molar). A few more definitions to start off with. When we write concentration, we very specifically use square brackets to mean the concentration of, in this case, sodium chloride. So this says the concentration of sodium chloride equals 2 molar. A capital M is reserved for the units of concentration, which is a shortening of moles per litre. So capital M, very specifically, moles per litre, and it's quite important not to confuse it with mass or number of moles when you refer to a solid, something like that. So concentration moles per litre. Moreover, and in example 2 I'll highlight this again, when we refer to the concentration of an ionic material, we refer to the concentration of the whole material, a solute. What this says is that in this instance we have 2 moles of sodium chloride in 1 litre of solution. Well, how do we work out the mass in grams? We need our formulas. Maybe I write them again here. Firstly, concentration is moles over volume in litres, and the formula that we have used extensively this morning is moles is mass over molar mass. In all these calculations, you generally have 2 knowns and 1 unknown. In the data that we're given a volume and a concentration. We need to find a mass. We can calculate a molar mass by looking it up on the periodic table, but we can't use this second equation directly because we don't know the number of moles. We use the first equation to get the number of moles. If I rearrange that first equation to give us a value of moles is concentration times volume in litres, I put in the values that I'm given my data. 2 moles per litre. I'm actually going to express the units, instead of capital M there, I'm going to put moles per litre, because in a lot of calculations, I like to put the units that I'm using in at least one line of my calculation so that I can check that they're all compatible with one another. For example, I might then take the raw data and say volume of 500 millilitres. But a warning bell should go off and say, we've got two different types of volume units there, millilitres and litres. I need to convert one of them so that it's the same scale as the other one. And it's like adding, let's say 2 millimetres to 1 metre, getting the sum of the numbers as 3 and expecting to get a meaningful result. You can't add or manipulate quantities unless they're incompatible units. What I need is the volume in litres, and I can convert millilitres to litres by dividing by 1,000. Maybe that's going to be the easiest way to do that. And in that case, I now have a quantity in litres. If I look at what's happening to the units, litres and per litre will cancel out. I will get a figure that I get from the calculator, 2 times, sent out as 0.5. I can actually work that out in my head, equals 1. And I get a unit. In this case, it's moles. That is what I want to get, because that's the amount I'm calculating. Okay, so trivial calculation, but I want to do it to specify the units. I've now got the amount of moles present, and I'm in a position to calculate the mass. Once again, I'm going to rearrange this second equation, so I get it in terms of mass equals moles times molar mass in my data. I've got 1 mole. The molar mass of sodium chloride is something I look up on the periodic table. Sodium is 22.99, chlorine is 35.45. Added together, I get a molar mass of NaCl as 58.4 grams per mole. If I check on what's happening to the units, moles and per mole will cancel, and I'll end up with a numerical value. My calculator says it's 1 times that, trivial calculation, and then units of grams. So my answer then works out to be 58.4 grams. I find that with solution calculations, it's actually easier to do the calculations line by line. There isn't a good table that I've worked out to use like the table we used this morning. I also find it's actually, in the long run, much better if I specify exactly what each line is. So take a moment or two to put in a few words there. Well, let me work through example 2, and then I want to show you something. And in example 2, top of page 2 of this topic 10, we have to calculate the concentration in moles per litre of a solution containing 45.2 grams magnesium chloride in 800 mils what is, let me rephrase the question, what is the concentration of magnesium chloride in moles per litre? Square brackets there. Once again, I'm going to be using those two formula. The information that I have to start off with is a mass. I can look up a molar mass so that the first cycle of this calculation is to calculate an amount in terms of numbers of moles of magnesium chloride that I have. So an amount in moles is mass over molar mass, 45.2 grams, divided by the molar mass of magnesium chloride, and magnesium is 24.31 plus 2 times 35.45 for chlorine, and they're in grams per mole. If I work out that, I find that I get a number on the denominator of 95.21. 45.2 divided by 95.21 is 0.475 moles. And what I always do with these calculations is, having got a figure, I look at it and think to myself, is that reasonable? And in many cases you'll be able to say, yes, it is reasonable, or no, that looks a little bit off, let me go and do the calculation again. What I mean by that is, we've got a number of about 45 on the top. We've got a number of about 95 on the bottom. 45 is half 90. So if I divide 45 by just over 90, I'm going to get a figure that's just under half. So yes, I'd say to myself, that figure is reasonable. And that can actually solve a lot of problems, because occasionally if you're working fast, you're working under pressure, you mistype a number on the calculator, this comes out as 0.00475, and if you progress with that, you'll get a completely wrong answer. So that can be useful. What's my aiming point? What is a calculation of magnesium? What is a concentration of magnesium chloride? I now have a number of moles. I divide it by the volume in litres. I have got a measurement here in millilitres. I need to convert that to litres. Doesn't matter whether I say 800 divided by 1,000 litres, or whether I jump straight to the value in litres. I would look at that and say it's about 0.4 over 0.8, so it's going to be sort of around about a half, not quite, because that's a little bit bigger than 0.4, so I must bear that in mind in my actual answer. Numerical answer, which turns out to be 0.594. I get units of moles per litre. It doesn't matter whether I express them as moles per litre like that, or even moles per litre like that, or as capital M for molarity. All ways of expressing them are correct. Now, back a moment to this business about the concentration referring to the solute. Now, you don't specify whether this is a gas, a solid, a liquid, or an aqueous. Of course, we're dealing with solution chemistry, so we're looking at aqueous solutions. But I don't put AQ here, because for the reasons we discussed before, it's not really chemically sensible to think of AQ behind magnesium chloride. It would suggest that you have this species, MgCl2, that's equated in water. We know that when magnesium chloride dissolves in water, the ionic material breaks up and you have magnesium ions separate from chloride ions. I could go on and write the ionic equation for, say, dissolving magnesium chloride, and now if I come back to the concentration, you can see why it is we need a convention to indicate what the concentration refers to. And the fact it always refers to the solute. So the concentration of magnesium chloride we've calculated, 0.594 molar. If we look at the concentration of the individual ions now, we can see that the concentration of the magnesium ions in solution will be the same numerical value, 0.594 molar, because dissolving 1 molar magnesium chloride gives 1 molar magnesium ions in solution. However, it will give 2 moles of chloride ions in solution. So that the concentration of Cl- in solution is going to be double this figure, 1.188 molar. So it's quite important to specify, if you're interested in a particular ion, whether you're referring to a concentration of that ion or whether you're referring to the solute. If you're given a concentration problem, then I can think of no instance where it won't refer to the concentration of the solute. Okay, let me show you something associated with concentrations. We might ask ourselves, how sensitive are your eyes? What sort of quantity, how small a quantity can you see? And for this, I'm going to just take some equipment that we often use for volumetric analysis, as we call it. This is involved in determining amounts of materials. I have some potassium permanganate here. That's actually 0.4 of a gram of potassium permanganate, and I'm going to dissolve it in water. It's purple, as you see. In the old days, in dentists, you used to, and maybe some dentists still do, you have a basin beside the chair, and after the dentist has crammed a couple of tennis balls in your mouth and all that sort of thing, he asks you to rinse and spit, and the solution they have beside the little sink there is a pink coloured water, and the pink coloured water is actually a dilute solution of potassium permanganate. It's a sterilising solution, antibiotic solution. It's not used quite so much now, but if you see a pinkish solution that's used as a sterilising agent, the chances are it's potassium permanganate. So what I hope to have done at this stage is dissolve that solid. Feel a little bit of grit still left there. I'm going to pour it into a volumetric flask. This flask is calibrated to give a precise volume at 20 degrees centigrade. I've still got a little bit of the solid left, so I'll just top it up with water there. Of course, I've chosen this material because we can see it rather than something that's white, because what I want to do is see just what sort of a concentration our eyes are able to detect. Yeah, well, that's pretty much done. What I am now going to do is top up my flask to the calibration line with water. Some days are better than others. And you won't be able to see it, but just there is a very fine line which indicates that this flask, if topped up to that line, the bottom of the meniscus of the solution contains exactly 250 mils of solution. And what I want to do now is just work out what the concentration of potassium permanganate is in that solution. Clearly a very dark colour. I started off with 0.4 grams. Don't worry about copying this down. It's not in the book, but I just want you to get the idea of what's happening. Potassium permanganate has the formula KMnO4. K plus, MnO4 minus. It's one of those polyatomic ions. The molar mass of potassium permanganate is 158.04. Let's call it 158. The number of moles, the amount that I have in terms of the number of moles is the mass divided by the molar mass, and that works out to be 0.0025 moles. The concentration that I have in that first volumetric flask, therefore, is 0.0025 moles divided by the flask, a 250 milliliter flask. 250 millilitres is the same as 0.250 litres. And, look at that. Concentration has come out to be a nice figure, 0.01 molar. Okay, it's no problem particularly weighing out 0.4 of a gram. What I can do is now take this, a pipette which is calibrated to give us exactly 25 millilitres of solution. If I draw up the material to a calibration mark up here. That needs a little bit more suck on it there. What I'm going to do is actually overshoot the mark. Oops. Put my finger on there, just lower it to the. So actually, that's the mark. Deliver exactly 25 mils to my next flask. And these pipettes are designed so that you allow them, you allow the solution to run out, you touch the tip on the glass, and then leave it. There is a drop left in, and that's accounted for in the calibration. So that's exactly 25 mils in there. Let me add water. I'm going to almost top it up to the line. And then my leaky bottle, make sure that I can top it up to exactly the correct amount. Once again, I've got a deeply purple solution. Having taken 25 ml to one solution, diluted it to 250 mils, I found that my potassium permanganate solution in flask 2 is going to be 1/10 of the concentration in flask 1. So I'm now down to 1/100th of a molar. Let me do this another time, and I'll try and speed up here. We have clean pipette. That's how it should be done. Allow that to run out. Top up my flask, almost to the line. If you overshoot, then you're in real trouble, you've got to start again. Do the final topping up with the bottle at eye level there, and quick shake. What I find is I still have a very distinct colour there. My concentration in flask 3 is going to be 1/10 again, so I could express that as 1 times 10 to the minus 4. I could express that as 0.0001. Let's do this another time. We can still see it very distinctly. Imagine that if I had to make up this solution from weighing out material, 0.4 grams is good for the first flask, 0.04 grams there, 0.004 grams, and it's getting very difficult to measure that amount. So by a series of dilutions, I can end up with a solution that has very little material in it, far less material than I could possibly have measured out accurately using a conventional balance. So in this fourth dilution, we still have enough colour that we can easily see it. Oh, wrong. There we go. Oh, running out of flasks here. However, and pipettes. Let's try this one more time after I put the concentration on the board. So in solution 4, we're at 1/10,000th of a molar concentration. And I think this will probably be about our limit. Here the graduation is way up here. There we go. .4 of a gram, 0.04 of a gram, 0.004 of a gram, 4 milligrams that is, 0.4 of a milligram, 0.04 of a milligram. So this is 40 micrograms of a material in 250 mils. And there's still a bit of a pink colour, at least from here. Maybe I need to actually remove that from the other rather darker coloured materials, and you can see that there is still a slight pink colour. So our eyes, at least for this compound, can detect a material that has a concentration down to well, it's kind of down, it's about 1/1000th of a molar or something, isn't it? One times 10 to the minus 6 of a molar, and still our eyes can detect that. I suspect we wouldn't be able to detect a 10 times dilution further on from that. Okay, let's get back to another couple of these examples that I want to show you, and I want to look first at example 3, and I will do that over here. What we have in example 3 is a scenario where we have to determine a volume. In other cases, we've determined a mass, we've determined a concentration. In this case, we're determining a volume. What volume of 0.450 sodium carbonate contains 10 grams of this solute? The formula for sodium carbonate is Na2CO3. The concentration of sodium carbonate in this example is 0.450 molar. The solute is always the solid bit of the material. Experiment we've just done, the solute was the potassium permanganate solid, which I dissolved in water to give a solution of potassium permanganate. Well, how do I start here? What I might do is actually write down my two equations that I might need, the amount or the number of moles, mass over molar mass. The other equation was concentration equals moles over volume. Now, let's see what the aiming point of my question is. I need to end up with calculating the volume. I have the concentration, but I don't have the number of moles. I have a mass. I can work out a molar mass, and hence I can work out a number of moles. So my first step is going to be working out an amount in moles that is equivalent to 10 grams of sodium carbonate. So in this case, the molar mass of sodium carbonate, 2 times my Quest 2.99 for sodium, plus 12.01 for carbon, plus 3 times 16 for oxygen. Will be the molar mass of sodium carbonate. That actually works out to be 0.0943 moles. Seeing what's happened with the units, grams on the top cancel with grams on the bottom. Per mole on the bottom is equivalent to moles on the top of the equation. So I now have a number of moles of material. I have a concentration. I'm going to rearrange this equation so that I have it in terms of volume. Volume is moles over concentration. I can now put in my values. I have 0.943 moles. I have a concentration of 0.450 moles per litre. If I look at what's happening to the units, the moles will cancel out. Per litre on the bottom translates into litres on the top of an equation. I do this calculation. What is it going to be about? I say to myself, oh, 0.09, let's think of that as 0.1. 0.1 divided by 0.4, 0.5, it's like kind of a quarter, a fifth. That's what I expect my answer to be round and about. I find that I get a numerical value about a quarter of a litre. I get a units which are litres. I can leave my answer as that, and that would be correct. Or I could, if I wished, say that that's equivalent to 210 millilitres. What I can't really do, shouldn't do, is say 0.210 equals 210. That's nonsense. What is correct is 0.210 litres equals 210 millilitres. So it's really quite important to be fairly rigorous about including the units in these cases. Now I want to do another experiment just before the next calculation. And as we're on to solution chemistry, I had to make up this little bit of a rush before the lecture, so I'm not quite sure what exactly is going to happen. But what we have is a number of beakers. And I have what you'll see labelled the magic jug. So what I'm going to do is pour my magic jug into these beakers. There's a litre solution here, so I'm actually going to put 200 mils. Well, that's not a very exciting one, is it? Into each one. So I've got a kind of a pink stuff, I've got red stuff, I've got something about liquid gold. Yeah, it's pale yellow, pale blue, pale clear. Okay, so my magic jug, the one solution gives me a range of colours. And if it's truly magic, then what I could do is put all these back in here. And the colours disappear again. So yes, there is a bit of magic there. Okay. Well, looking at a more serious side of solution chemistry, what I'd like to look at is example 4. Example 4 actually typifies a sort of experiment called a titration that is quite commonly used in an analytical laboratory. It enables you to find out about quantities, about concentrations of a solution of unknown concentration from reaction with a solution of a known concentration. And very typically, this involves the reaction of an acid with a base. And we look at acid-base reactions in detail in topic 13. But the scenario here is that we have a solution of sodium hydroxide of unknown concentration. Sodium hydroxide, the concentration of sodium hydroxide is unknown. And we do this technique called titration, which is a type of reaction, against a standard sulfuric acid solution. By standard, we mean one of known concentration. And we find that the standard sulfuric acid concentration is 0.104 molar. We're also told that if we take 25 millilitres of the solution of unknown concentration, it will react exactly with 20.05 millilitres of solution of known concentration. What we want to do is find out this. Now, for people that are familiar with maths, you might be able to say, oh, well, we can do ratios and get the answer very quickly. But be careful, because it might not be a one-to-one ratio of reactants. Now, the first stage in any calculation involving a reaction is to write the balanced chemical equation. And if I do that, sulfuric acid reacting with sodium hydroxide, you need to know a little bit about the products, and I don't expect you to know them at this stage, but the products are water and sodium sulfate. And I can see from the equation that sodium anyhow, the Na bit, is not balanced. 2 sodiums on the right, I need 2 on the left. If I now look at what happens with, say, the OH, I have 2 lots of OH. They will react with 2 lots of the H from there to give me 2 lots of water, i.e. 1 mole of H2SO4 will react exactly with 2 moles of sodium hydroxide to give 2 moles of water and sodium sulfate. But how many moles of sulfuric acid do we have? And this is how I tend to do the calculations. The number of moles of H2SO4. Well, how do I calculate this? Thinking of the equations we've been using today, summarising concentration is moles over volume, or put another way, taking volume over to the other side, moles is concentration times volume. I want the number of moles of sulfuric acid, so that's going to be the concentration times the volume. I need the volume in litres to be compatible with the concentration units. There's a number of ways I can do this. I can convert it in my head and say 20 millilitres is 0.02005 litres, or I can take that figure and divide by 1,000. I work this out, I get a numerical value, which in this case is 2.085 times 10 to the minus 3. Per litre, and the litres cancel out, so the units are moles. So, in this reaction, I've used exactly 2.085 times 10 to the minus 3 moles of sulfuric acid. Now we can see that from the equation, this will react with twice that amount moles of sodium hydroxide. And if I was just to calculate that out, twice of that, 4.170 times 10 to the minus 3 moles. So I've now got the number of moles of sodium hydroxide that has reacted in this equation. I've got a moles, I've got a volume of sodium hydroxide, so I'm now able to calculate a concentration of sodium hydroxide, which is what I want to answer my question. So the concentration of sodium hydroxide, number of moles, 4.170 times 10 to the minus 3, divided by the volume in litres. I have a volume up there in millilitres, so I'm going to convert that in my head to litres by dividing by 1,000. That value comes out to be 0.025 litres. If I do my calculation, I get a figure .167. It's a numerical figure, and I get a value of units of moles per litre, or molarity, capital M. Quite an involved calculation, but it focuses just on one formula. Personally, I remember only concentration is moles over volume, and then I rearrange it if I need to. I don't try and remember all the rearranged forms. What I do is think to myself, what data have I got? What do I want to know? What is the aiming point in my calculation? Write a balanced equation as the first step. Write out words that indicate what's going on in the various calculation steps. Okay, that's it for the lecture.